All right, in the last lesson, we talked about the fundamental counting principle, which said for each task that you're trying to complete, you determine how many possible outcomes there are, and then multiply all those together for each task. And that's how you get the total number of possible outcomes. And remember, we talked about that man with the ties in the pants and the shoes and the shirt. It didn't really matter which order he chose those things. And so we just multiplied all the possible options together and got our answer. But today we're talking about something called permutations. And permutations, the order does matter, right? So here's the mathy definition. A distinguishable permutation is the number of ways that R objects selected from a set containing n unique elements can be placed in an ordered arrangement. That's a lot of mathy words. I'm going to break that down for you here in just a bit. But we do have this formula right here for figuring this out. So yesterday's formula was just you figure out how many options you have, like when we did the flip a coin. This is our first flip, our second, and our third. And we had two possible outcomes for each one. We multiply and we got 8 possible outcomes. Well, that was not an ordered arrangement, so we could do that. Today we're talking about permutations, which is an ordered arrangement. Like the order matters. One order is different from another order. And when that happens, we call it a permutation, and we have this formula. We also have this notation for that, which we're going to talk about. Whenever we use the word unique in mathematics, we are saying that there's no repetition involved. Everything is unique. And just as a side note, yesterday we talked about an exclamation mark as meaning factorial. When you're writing mathematical proofs, an exclamation mark can also mean unique. In my upper level math courses when I was in college, I wrote proofs upon proofs upon proofs, and we very often would start a proof as saying there exists a unique element such that blah, blah, blah. Anyway, the exclamation mark would stand for unique. So there's different ways of symbols in math, of using them. At any rate, so no elements repeat. And if we're looking at this notation here, the NPR, it does not stand for National Public Radio. The N stands for the number of elements, in the set that you're dealing with. Remember, the set contains all of your possibilities. And the R stands for the number of elements being picked out and arranged. Okay, so maybe you have like 6, you're working at a restaurant and you have 6 fruits to choose from. You're going to make a fruit salad by picking 4 of those 6. How many different arrangements can you make? This is sort of what we're getting to, but first in this example, we're just going to practice the formula before we get to actual problems. So we have 3 examples. And all the only point of these is just to practice with the formula. So the first one is 10p7. So the 10 is the n value in the formula, and 7 is the r. And so if we're just plugging those in, so n equals 10, r equals 7. So you have 10 things, you're picking 7 of those, and you want to know how you can order those and what kind of arrangements. we're just going to plug it into the formula. We have n factorial on top over parentheses n minus r, which is 10 minus 7 factorial on the bottom. So what does that mean? It means on the top, it means we have 10 times 9 times 8 times 7 times 6 times 5 times 4 times 6. Okay, that took a lot. And then on the bottom, we have 10 minus 7, which is 3 factorial. So that's just 3 times 2. Well, I want you to notice something here. The 3 factorial repeats on the top and bottom. So we can just go ahead and cross those out. And then when you go ahead and multiply the top 10, 9, 8, 7, 6, 5, 4, you get 6,000, 60,000 for, goodness gracious, 604,800. And I want you to pause your video and take a moment and do the next 2 examples. All right, I deleted my work to give myself some room. In this next example, n equals 9 and r equals 6. So that gives me 9 factorial over 9 minus 6 factorial, which means 9 factorial over 3 factorial. This time, when I write out the 9 factorial, I'm going to stop when I get to the 3. Watch. So I've got 9 times 8 times 7 times 6 times 5 times 4 times 3 to 1 is just 3 factorial. And that's just going to save me some writing because I know that, just like in the last problem, the 3 factorials cancel out, leaving me again, or with 1 0 less, 60,480. And for the last one, n factorial on top makes 6 factorial. On the bottom, it's 6 minus 3 factorial. So that's 6 over 3. And when I expand 6 factorial, I'm going to stop at the 3. Because again, I know it will cancel out with the 3 factorial on the bottom. And 6 times 5 times 4 is 100. All right, so that's practicing the formula. Let's do some examples now. All right, we'll do this next example 2 ways. We're going to use the method from our last lesson, and then we're going to use this formula. And you'll see that we get the same answer either way. So it says the local chapter of Mu Alpha Theta will soon be electing a president, vice president, and treasurer. In how many ways can the positions be filled if the chapter has 15 members? So let's talk first about why this is a permutation. The reason is because you have to take the unique elements, meaning there's no repetition, right? These are human beings we're talking about. You can't have one person be the president and one person be the vice president, right? There's not. They're unique from each other, they're different, and there's not repetition. And that's what an ordered arrangement means, okay? And so we have, if we're using our method from the last lesson, there are 3 tasks that need to be filled or completed. We've got to choose a president, a vice president, and a treasurer. How many options are there for the president? There's 15, right? Because there's 15 members. But once you place a person in that position, they are no longer available for the other one. So there's no repetition allowed here. So once you place someone as the president, there are 14 people left to be chosen for vice president and 13 for treasurer. And we learned yesterday that when you're using the fundamental counting principle, you multiply those numbers together and you get 2,730 ways that you can fill those 3 positions out of 15 possible people, okay? Now let's do this using our permutation formula. So remember, this is NPR, where N stands for the total number of elements in your set, which for us was 15 people. And we're going to find a permutation of that, which means we're creating an ordered arrangement of those 15 people, and we're choosing 3. We're choosing 3 people from that set, and we're making an arrangement of them. So n factorial is the top of our formula, which here in this case is 15, and the bottom is n minus r, which is 15 minus 3. So that's 15 factorial over 12 factorial, which is 15 times 14 times 13. I will stop at 12 factorial because it will just cancel with the 1 on the bottom. And guess what we have right here? 15 times 14 times 13, which is the same thing we had with the counting principle. So let's talk about these next examples. Example 2, there are 7 horses in a race. In part A, we're going to see how many ways can the 7 horses finish the race. All right, so I'm telling you this is a permutation. So we'll do our NPR. How many possible, so N stands for the number of elements in the set that you're talking about. Well, our set is 7 horses, so there are 7 to choose from. And R stands for the number of elements we're picking out and arranging. Well, in this case, we're talking about all 7 horses. We want to know about each of them, where they're going to end up. So we are picking 7 of those 7 and figuring out the different ways we can arrange them. So if you were using your permutation formula, it's n factorial on top, n minus r factorial on bottom. And I want to point out something to you. 7 minus 7 is 0. And what did we say in the last lesson that 0 factorial was defined as? 1, right? So really what's happening here, if you're using this permutation formula, it's 7 factorial over 1. We don't really have to worry about the over 1. So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And please notice, I could have used the counting principle from yesterday to do this. That would have looked like this. How many horses could have been in first place? How many horses could have been in second, in third, fourth, fifth, sixth, seventh place? So whether I did the permutation formula or the counting technique from yesterday, it still would end up as 7 factorial, which is 5,040 ways. So take a minute and pause your video and read example B. So then it says, in how many ways can the 7 horses win, place, or show? Meaning, how many different ways can they get first, second, and third places? Solve using 1, the fundamental counting principle, and 2, a permutation. So we'll do fundamental counting principle first. Okay. How many tasks are being completed? Just 3. First place, second place, and third. There are 7 horses that can finish first. Once that horse is decided, there's 6 for second and 5 for third. And we just multiply those together and we get 210 ways. And then we'll use the permutation formula for our second method. It's out of 7 horses, we're choosing 3, and seeing how many different ways those can be arranged. So that's 7 factorial over 7 minus 3 factorial, which is 4 on the bottom. So 7, I'm going to just expand the factorial until I get to 4, and I'll stop there because those will just cancel, and then I'm left with 7 times 6 times 5, the same thing I had with the counting principle method. Okay. So on the second part of your notes, I want you to go ahead and try that example 3 on your own. Pause the video and try that. An art gallery has 9 paintings from an artist and will display 4 from left to right along the wall. In how many ways can the gallery select and display the 4 paintings? I want you to try this using fundamental counting principle or the permutation formula, whichever method you like best. I will show you both of them. For the fundamental counting principle, there are 4 things that need to be decided. Where the first painting, which ones, or I'm sorry, I should say, which of the paintings is going to go first, which second, which third, and which fourth. And there are 9 options for the first one. Once that's been decided, there's 8 options next, and then 7 and 6. Okay, when you multiply, that will give you 3,024 ways. And if you were doing your permutation formula, it's 9, choose 4. So 9 factorial over 9 minus 4 factorial, which is 9 factorial over 5 factorial, which is 9 times 8 times 7 times 6 times the 5 factorial, which cancels with the 1 on the bottom. So that cancels. So 9 times 8 times 7 times 6, again, we know is 3,020. So those permutations we just did are where all the elements of the set are unique, like the people for the president, the vice president, the treasurer. That set was made up of people, and all of those people are different from all the other people, right? Or the horses, they're each unique from each other. There's nothing repeating within the set. So now we're going to talk about, well, what happens with permutations when something is being repeated in the set? Not elemente, but elements. What happens if the elements of the set are not all unique? Okay? This means that there's repetition among the things that you're choosing from. So in that case, we have another formula, and it looks like this, okay? So just like before, the N stands for number of elements in the set. But P, Q, and R, by the way, not all problems will have P, Q, and R. Some problems might just have P, and some problems might just have P and Q. It depends on how many things are repeating in your set. So P stands for example, 1 element, and how many times that element is repeating. Let's say there's only 1 thing repeating. That would mean you don't need the Q and the R. let's say there's 2 things repeating in your set. Then you would just need a P and a Q. You would need P, Q, and R if 3 things were repeating. If 4 things are repeating, you would have to add 1 to this formula. Okay? So this formula changes a little bit depending on your particular problem that you're doing. The N, though, will always represent the total number of elements in your set. So let's look at these examples. It says in example 4, how many unique permutations can be formed from the letters of the given words? So in example A, I have this word leave. Well, I want you to first figure out your N. What are the total number of letters in that word? There's 1, 2, 3, 4, 5, right? There's 5 letters. That's supposed to be letters, just a number. N equals the number of letters, which is 5. Now let's talk about how many things are repeating. How many letters do you see repeating? There's 1 letter that repeats, and it's E. So I just need a P value here. P equals the number of times E repeats, which is 2. So then here's how our formula will look. It's n factorial on the top, so that's a 5. But we have to divide out the factorial for the number that's repeating. There's one letter repeating, sorry, I said number, and it's repeating twice. So we only need the P factorial. There's only 1 thing repeating, so we only need the P. We don't need 2P, we just need the P. So I'm going to stop at 2 factorial here because it cancels out with the 1 on the bottom. Multiply, and you get 60. So there's 60 ways. All right, I want you to try example B. Pause the video and try it on your own. All right, so this word levy is very similar to the word leave, right? There's no A though. The N value here, the number of letters altogether, happens to be the same, which is 5. How many letters do you see repeating? 1 letter repeats, right? E. So there's only 1 thing that's repeating. How many times is it repeating? 3 times, right? It occurs 3 times. So we set up our permutation formula. There are 5 things, and we're choosing 3. Oh, sorry. That's not the right formula. It's 5 factorial over the 3 factorial. So it's 5 times 4 times 3 over 3 factorial. The 3 factorials cancel, leaving me 5 times 4, which is 20. There's 20 ways. Okay, and then we get to these last 2 examples. Assuming all multiple births are identical and the children cannot be told apart, how many distinguishable photographs can be taken of a family of 6 if they stand in a single row and there is, example A, 1 set of triplets, or example B, 2 sets of twins. So there's a lot going on in this problem. Let's sort of break this down. We got a family of 6 people. They're going to be taking photographs. If any of the people, if there were any multiple births, like triplets or twins, assume that they are all identical. Okay, they're not, fraternal twins look different from each other. So we're going to assume they're all identical, so they look exactly the same. You see where we're going with this? Just like E repeated in the previous example, here a person is repeating. As far as the photograph is concerned, we're all unique individuals with our own identities and souls, of course. But if we're looking at a photograph, then everyone's just the same if they're identical twins or triplets. And so they're basically just elements in the set that are repeating, right, as far as a photograph is concerned. So we are going to figure out how many different ways these 6 people can stand in a photograph and it's distinguishable, meaning you could tell the difference. And we're going to do that assuming in example A that there's 1 set of triplets, or in example B, there's 2 sets of twins. So your N is still going to be the number of elements total in the set. Well, that's how many people there are in the set. The set's the family. The elements are the people. So there's 6 possible, or there are 6 elements in the set, okay? If you have triplets, how many of the elements are repeating? 1. Just like in the previous example with the E, there was just one thing repeating, the E, but the P stands for how many times it was repeating. So this one person who looks the same as far as a photograph is concerned, there's just one, but it's repeating 3 times, right? There's just one element that looks like that. And there happens, or there's, I should say, there's just that one look and it's repeating 3 times. And so then here's how the formula goes. It's n factorial over p factorial, which is 6 over 3, which is 6 times 5 times 4 times 3 factorial over 3 factorial. The 3 factorials cancel, and 6 times 5 times 4 is 120 different photographs, 120 ways. But what about if instead of 1 set of triplets, there was 2 sets of twins? So here's where we are going to need more than just P on the bottom. So the N stays the same. There are 6 elements in the set, meaning 6 people in the family. But there's 2 things repeating. So I need to put a Q into the formula. One thing is repeating twice, because that's what twins are, right? 2 look the same. And the other set of twins, which is Q, is also repeating twice. And so when we go set up our formula now, we have 6 factorial on top again, and then the P factorial on the bottom, which is 2 factorial, times the Q factorial on the bottom. And here's how that looks expanded, okay? 6 times 5 times 4 times 3. I'm going to stop at 2 factorial because that's what I have on the bottom. That cancels with only one of my 2 factorials on the bottom. And then that gives me 6 times 5 times 4 times 3, which is 360, over this leftover 2 factorial on the bottom, which is just 2. And that's 180 ways. Okay, so go do your practice problems and turn them into Google Classroom.